Right now, somewhere inside your lower back, there's a small triangle of bone sitting at the base of your spine. Most people never think about it until they slip on ice and land directly on it. And if you've ever done that, you know it's one of the most uniquely awful pains the human body can produce. That bone is called the coccyx. And it's not just a bone, it's a fossil. Not a fossil in the ground, a fossil still attached to you, right now, made of your own cells. It's the last surviving piece of a tail your ancestors used to have. So here's the question. If having a tail is so useful, and it clearly is, just look at almost every other mammal on Earth. Why don't we have one? Why did evolution, at some point, decide that the human body was better off without it? For most of the time scientists have studied this, the honest answer was, we don't actually know. It was one of those questions that sat in the interesting but unsolved pile for over 150 years. Charles Darwin himself wrote about it in 1871 and basically shrugged. But in 2024, a team of researchers in New York finally cracked it open, and the answer involves a broken piece of DNA, a series of mice born without tails, and a trade-off so strange that the scientists who found it almost didn't believe their own data. Let's get into it. Here's something most people don't know about themselves. At some point, you had a tail. Not metaphorically. Actually, around the 4th to 5th week after conception, every single human embryo grows a tail. It's got actual vertebrae in it, 10 to 12 of them, stacked up just like a vertebral column. For a brief window in early development, a human embryo looks remarkably like a tiny tadpole with a tail trailing off the end of its spine. Then, around week 8, it disappears. The tail tissue gets reabsorbed back into the body, and what's left fuses into that small triangular bone we mentioned, the coccyx. Your tailbone isn't a separate, unrelated structure that evolution just placed there. It's literally the leftover base of a tail that started growing and then got switched off every single time a human is built, generation after generation, for millions of years. Every now and then, the switch doesn't fully turn off. There have been documented medical cases, fewer than 30 in recorded history, of babies born with what doctors call a true vestigial tail. It's soft tissue. It can even move a little because it has muscle in it, though it has no bone and serves no function. In almost every case, it's surgically removed shortly after birth. So the blueprint for a tail is still in our DNA. It still gets partially built every time a human is made. We just don't finish the job anymore. The question is, when did we stop, and why? This part of the story starts with a guy named Bo Xia. Xia was a graduate student in stem cell biology at NYU, and according to his own account, this exact question, "Where did my tail go?" had been bothering him since he was a kid. Which is a strange thing to be bothered by as a child, but it turned out to be the right kind of strange, because it eventually led him to one of the most talked about discoveries in evolutionary biology of the decade. Here's how the science world had thought about this for decades. Researchers already knew that humans and apes, chimps, gorillas, orangutans don't have tails, while monkeys do. Somewhere around 25 million years ago, the ancestor we share with modern apes branched off from the ancestor we share with tailed monkeys, and in that branching, the tail vanished. Scientists had also identified over 100 genes connected to tail growth in different animals, from mice to lizards to fish. So the genes for build a tail clearly still exist somewhere in our genome. Something had jammed the machine. Xia's idea was simple in concept, but enormous in scope. Take the DNA of tailless apes, 6 species, including humans, and compare it directly against the DNA of 9 species of tailed monkeys. Somewhere in that comparison, there had to be a difference, a mutation that apes have and monkeys don't. And there was. It showed up in a gene called TBXT. Now, TBXT isn't some obscure, irrelevant gene. Its nickname is actually brachyury, Greek for short tail, because scientists already knew it played a central role in tail development across the animal kingdom. Mutations in this same gene are the reason some breeds of cats, like the Manx, are born without tails. It's the reason certain lab mice naturally come up tailless. This gene was already a known suspect. What Zia's team found inside it was something almost poetic in how small and accidental it was. Buried inside TBXT, they found something called an ALU element, a short, repetitive snippet of DNA that's sometimes nicknamed jumping DNA, because these little sequences can copy themselves and insert into new locations in the genome over evolutionary time. Most of the time, when one of these jumps into a gene, nothing dramatic happens. It's genetic background noise. But this particular jump landed in just the wrong spot. There was already another ALU element sitting nearby in the gene, pointing in the opposite direction. When the new one inserted itself, the two of them ended up facing each other like mirror images. And when the cell tried to read the gene and build the RNA instructions from it, those two opposing ALU sequences paired up with each other and folded the RNA into a loop that caused an entire section of the gene's instructions, called an exon, to get skipped over entirely during the assembly process. Think of it like a recipe card where 2 corners of the paper accidentally stick together and fold a whole step out of view. The cook never sees that line of instructions. They're still in the recipe, technically, just permanently hidden by the fold. That's roughly what happened inside the TBXT gene. One critical instruction for building tail structure got physically folded out of the reading process. And here's the detail that makes this such a strong piece of science rather than just a hypothesis. The researchers didn't stop at finding the mutation. They went and engineered that exact same genetic change into mice. And the mice that received it were born with a range of tail effects, some shorter tails, some no tails at all. They had recreated, in a living animal, in real time, the same genetic event that may have happened in our ancestors 25 million years ago. Here's where this story stops being a clean, satisfying answer and turns into something a lot more interesting, and honestly, a little sobering. When the researchers studied those tailless mice more closely, they noticed something they weren't looking for. A small but consistent increase in something called neural tube defects, birth defects connected to incomplete closure of the developing spinal cord. In humans, the most well-known version of this is spina bifida, a condition that currently affects roughly 1 in every 1,000 newborns. The gene that builds tails, it turns out, doesn't only build tails. Genes are rarely single-purpose tools. TBXT is also deeply involved in how the neural tube, the structure that eventually becomes the brain and spinal cord, properly seals itself during early development. So when evolution found a way to switch off tail growth, it apparently couldn't do so without nudging that other, completely unrelated system a little further toward malfunction. One of the lead researchers on the study, Itai Yanai, put it about as plainly as a scientist can. He said there must have been enormous evolutionary pressure to lose the tail, pressure strong enough that our ancestors essentially paid for it with an increased risk of a serious birth defect, and it was still worth it. That's a strange thing to sit with. Somewhere, deep in evolutionary time, losing a tail was apparently such a significant survival advantage that natural selection pushed it through anyway, defect risk included. We are, quite literally, walking around today with a slightly elevated risk of a specific birth complication because some ancestor of ours, millions of years ago, benefited enough from not having a tail that the trade was worth making. This is the part where we have to be honest with you, because the headlines after this study came out made it sound like scientists had solved the entire mystery. They hadn't, not completely. What the 2024 study nailed down was the mechanism, the how, the exact genetic glitch responsible for switching the tail off. What it didn't fully nail down was the why, meaning what specific survival pressure made a tailless body better than a tailed one in the first place. The leading idea, and it's a strong one, but still technically a hypothesis, connects tail loss to the shift toward life on the ground and eventually to walking upright. Many primates use their tails for balance while moving through trees, sometimes even for grip. As the ancestors of apes and humans started spending less time swinging through branches and more time moving on solid ground, a long tail may have become less of a tool and more of a liability, dead weight to carry, something to get caught on obstacles, energy spent, maintaining a structure that no longer pulled its weight. There's also a connection researchers have pointed to between tail loss and the eventual evolution of upright, two-legged walking, bipedalism. The two changes appear to be linked in the broader story of how our body plan reorganized itself for life on the ground. But scientists are careful here, and we should be too. Correlation in the fossil and genetic record doesn't automatically mean we've identified the single specific reason natural selection favored this exact mutation. The researchers themselves have said plainly that we may never know with full certainty what the precise pressure was, and that the reasons could even have been different across different mammal lineages that independently lost their tails throughout history. So if you came here wanting one tidy, complete answer, we genuinely don't have it yet. What we do have is the closest thing science has ever gotten, the exact broken piece of code, recreated and tested in a living animal, with a documented cost attached to it. That's not nothing. That's actually a massive leap from "we have no idea" to "we know precisely what changed. We just don't know with total certainty every reason it was worth it." Here's the part that always gets me about this story. Even after the tail disappeared, evolution didn't fully erase the instructions for building one. It just buried them. Your tailbone still anchors muscles you use every single day. The muscles that support your pelvic floor. The ones involved in basic things like sitting upright and controlling your bowels. An old, repurposed structure, still doing quiet, unglamorous work, decades after its original job became obsolete. And every human embryo still builds that little tail in the womb, every time, before erasing it weeks later. The instructions are still in there. The code for "grow a tail" never actually left our genome. It's just been folded shut by a tiny, accidental piece of jumping DNA that landed in exactly the wrong place, 25 million years ago, in some ancestor none of us will ever know the name of. It's strange to think about. Somewhere in your own DNA, right now, sits the broken instruction for a body part you will never have. Not erased, just switched off, so next time you sit down too hard and feel that very specific, very unpleasant jolt in your tailbone, that's not just an annoying bone. That's 25 million years of evolutionary history, still attached to you, still doing its job long after the rest of the tail disappeared. If you had the option, knowing what we now know about balance, grip, and how other primates use theirs, would you want yours back? Let me know down in the comments.